Hi folks, Mr. Thessalonian back here again. I'm working on the large 4-foot in diameter Wimshurst Electrostatic Generator project. What you see in front of you here is our mount towers and our drivetrain. It's very simple to build, all made out of 2x4s, something that you can get at home. This system is going to produce a lot of power. We should be able to get probably 10-inch arcs, I would assume, out of this, giving us upwards of 10,000 volts or more, depending on our capacitor sizes. So what we're going to do now is we're going to go ahead and take a rod across the two tops, and that's actually going to be where the two discs actually spin from, is right there on the top of these two towers. From right here you can actually see I've already got the lines marked to mount that up there. So then it comes down here to one 10-inch pulley down here. These are aluminum pulleys from swamp coolers you can find at any hardware store. I got another pulley still to put on there. I just got this all done. I'm kind of making sure that it's all spinning right, everything looks pretty free and even. What we've got here now is a 1-inch pulley on the end, is our drive pulley to the lower shaft, and these two will actually spin our disc. We'll have one belt looped opposite and one belt running normal, and that'll give us a dual directional spin on our disc. Now that runs up here from a 1-inch to a 14-inch in diameter aluminum pulley, and just the ratio between that 1-inch and the 14 is about 8.5 to 1. So you're basically able to get for every one turn I turn here, I get 8.5 turns here. Now with the 10-inch pulley going up to a 1-inch off of our Wimshurst disc, we should be able to add another 4 to 1 off of that or so, and bump us up over the 10 to 1 ratio, which will give us, you know, if I was turning this hand crank 1 cycle per second, that'd give us 600 rotations per minute on our lower drive or on our upper discs here. So let me go ahead and just walk you around here. These are all just pillow bushings here. You've got little grease certs at the top that you can put oil inside of them. The hand crank itself, I have designed loose like this because the inertia when you spin it will actually drop that handle, just like you saw, immediately back this way instead of grabbing your arm. This thing doesn't have a freewheel, which if you're going to build something this big, I just suggest putting a freewheel design in there. And you can see here, if I stop that, watch that lower pulley down there. I can get that thing just cruising. Still, now I can make it go backwards, at least in your visual spectrum there. So there you go. Very fast RPMs, just out of a simple hand crank turn here. Alright, so I thought I'd show you that. We don't have much left to do to the drivetrain other than to box it all in and cover a portion of this with a dielectric material. I'm going to go ahead and cover most of the face here with a dielectric, and even probably a dielectric cap over this just at the very center top ridge where the belts won't hit it. And that'll help keep some kind of barrier between our disc and any metallic object in here. You can see here the lines are, that's actually the lower center point of the disc. Will come down to about right there. So we got a little bit of protection we got to put against that face. I doubt we'll lose much, but if we don't cover it, it will be a loss in our system. So let me go ahead and finish the rest of this. I'll show you what it looks like when we get the top system all put across, and we'll start working on our Wimshurst discs, and I'll show you from there. Hi folks, Mr. Thessalonian back here again. I'm working on my really large Wimshurst Generator project right now. And what I'm doing at the moment is I'm building our backup low voltage generator built with Neodymium Magnets and standard coils, which is also the completion of our human powered generator project. Right now, as you can see right there, those are two large Neodymium Magnets on either side of this nice steel shaft here. I have some push bearings set into the board on either side that goes to our belt here. All the way down to a 10-inch pulley off to the opposite side where the two will run for our Wimshurst. We'll actually be able to engage and disengage this, so we can either use the Wimshurst or we can use a low voltage high amperage generator here. Alright, so all I've got here on this side is a chunk of nail plate for construction. It's just making sure the two magnets aren't flopping towards each other. I'm going to go ahead and drop another one on this side here. So here's my piece. These are a little difficult to maneuver around these larger magnets. So there we go. We'll have just two plates of steel, one on either side of those, and those are opposite polarities sticking out, a north and a south face. I'm going to real quickly just wrap a couple wraps of duct tape around this, that way they don't fly off of there when I spin it, because the RPMs that I'm generating, or at least the ratio from the hand crank over here all the way over to that bar spinning is 45 to 1. So it's a pretty high ratio. It's a lot of inertial force trying to spin those magnets free. So I'm going to go ahead and just wrap a few wraps on there of duct tape. And then what we have here, just real quickly set up, This is one of those nice big coils I like to wrap. It's just quickly duct taped on there. And I'll set that. If I can get down underneath here and show you, we'll rotate that magnet setup to about right there. And we should have just enough of an air gap that shouldn't touch. And if we need a little more, so there we go, should be able to see just barely an air gap right there. So we'll be able to prop that up, screw down this board up here, kind of mount that into position. And right now, what I have are 2 wires hooked to the meter here, up to our voltmeter. And what I'm going to do real quick is I'm going to tape that up like I said, and then I'm going to go ahead and spin this and show you the kind of voltage we can create with just a single coil and 45-to-1 ratio here at the hand crank. So give me just a moment. Alright folks, you should be able to see the meter here. Let me turn it on. We are set here to 200 volt max AC voltage. I'm going to give this thing a good healthy spin and let's see how high we can get the voltage on this. So there you go. Let's see what we ended up getting there. Should have probably seen real close to 16 plus volts. We can give that one more real quick spin, then I'll give you a shot of how fast I'm turning it on the handle here. So let me do that one more time. So there you go. That's actually what we're producing with a hand crank. So that's just 2 neodymium magnets in a single coil. And you can see the magnets spinning here in the background. So let me go ahead and set up the camera and show you real quick here just how fast it's actually rotating over there. Alright, you should be able to see the hand crank. I'm trying to get the meter still there. You should be able to watch the wheel right here in the shot. So there you go. You can probably see it's not turning all that fast to get that thing over here, our neodymium over there, actually just cruising. So let me zoom in just a little bit more and I'll show you some of what it looks like zoomed in. So there you go. There's a nice little measurement there. I'm going to start completing the actual generator itself, and I'll show you what it looks like when it's done. So there you go. That's our low voltage, high amperage human powered generator. This same system will also be our high voltage, low amperage system, the Wimshurst Generator also. So it'll be a tandem system. We can run one or the other, or we can actually do dual voltage experiments. Well, until next time, I hope you enjoyed. This is Mr. Thessalonian and the Thessalonian Man Show. Hi folks, Mr. Thessalonian back here again. I'm working on the low voltage DC side of our Wimshurst hand-powered generator here. And I showed you on the last video that we had 1 coil and 2 magnets on the rotor in there. So it'd be a little difficult to show you inside of there, but right now what I have is actually 4 magnets on the rotor, and it's not actually held on by duct tape. There's metal banding and everything. I just did that as a rub indicator just in case. I've got 4 coils now mounted all the way around those 4 magnets. As you can see here, I've got the 2 coils mounted on the tops and the bottom, and I've got 2 side coils mounted here on either side. You can see the wiring coming out of the coils here all wired together. I've got my positive meter hooked up here, and I've got my negative meter hooked up there. And like I showed you in the last video, the RPMs I'm actually creating inside of this machine is about 2,700 RPMs. I can get it going a little faster than that, but that's about the average that I'm able to produce with a minimal amount of effort out at the hand crank. So what we're going to do here real quick is I'm going to set up the meter so you can actually see it down in here and watch the action going on inside. I'm going to let you see the voltage that I'm actually able to create with just a simple set of 2 belts, 4 pulleys, and a hand crank. So this is giving us a 45-to-1 ratio, like I said in the last film. Let me go ahead and set that shot up, and I'll show you what kind of voltage we're able to create. Alright folks, so what I'm going to do now is I'm going to switch the meter on here. We are set to AC 200 volt max here on the meter, and I'm hoping that can show up pretty well. You won't be able to really see much going on inside of there, but you'll be able to hear the thing rotating. Let's go ahead and spin this and see what kind of voltage we're able to create. So here we go. So there you go. That should have been a pretty good measurement. I'm hoping there on the shot you saw somewhere close to 80 volts. Let me go ahead and give it one more rotation, see if we can't make sure that we've passed that 80 volt marker. There we go. So there's a brief demonstration of what 4 magnets and 4 coils can do at 2700 RPMs. So now that we've actually achieved the RPMs I was looking for, which is, pretty high RPMs for hand crank, we've also achieved a very high voltage. What I'm going to do now is incorporate a crossover board, or a peg board basically, that'll allow me to wire these coils all into it and change over with the jumper, whether I'm in delta or star wiring diagram here, which will increase the voltage like you see now, or decrease the voltage and increase the amperage. I brought 2 diodes to do a diode or an amperage test today. Both diodes ended up being bad, so we'll do that another time once this is completed. Hope you enjoyed. Until next time, this is Mr. Thessalonian. Hi folks, Mr. Thessalonian back here again. We're working on our 4-foot in diameter Wimshurst Electrostatic Generator right now. Before I glue this all together, I kind of wanted to show you what one of these look like, rough set and kind of dry. What we have here in the center is a brass bushing. That brass bushing goes all the way through the 3/4 inch piece of plywood there, and that's going to ride on our 1/2 inch shaft. Let me go ahead and just pull that piece of 1/2 inch plywood off of there carefully. Alright, so what you see here is our large Wimshurst 4-foot in diameter disc. You can see I've glued all our induction panels on there. We've got 32 induction plates. They're 9 inches long, and at the top width up there they're 4.5 inches wide, and at the bottom they're 3 inches wide. So we've got a pretty good LDW striker distance on all of this. So what we're going to do now is I'm going to go ahead and take some sandpaper, and I'm going to rough up the entire center surface of that plexiglass with a piece of sandpaper. That way when I put the wooden disc on there, the support disc, the reason I've got the support disc on this wheel and these 2 that I'm building right now is actually because this is 1/8 inch plexiglass, and at this diameter doesn't have enough strength to be used by itself. So I'm going to reinforce these 2 discs. I've got 2 others that are being made right now at 1/4 inch, and they won't need the same reinforcement. So on the other 2 that we're going to build, they're actually going to be 1/4 inch, which is actually going to give us more dielectric material, which will actually reduce the voltage slightly. The reason I did this at 1/8 inch was the voltage will be higher with the thinner dielectric that I have between these, obviously. So we're going to do 2 different setups. So in the end, we'll actually have 4 4-foot in diameter discs rotating. One, like I said, will be 1/4 inch material. One will be 1/8 inch with the supports. So let me go ahead and rough that all up. I'm going to glue that on, and I'll show you what it looks like from there. Alright folks, so here's what I want to show you now. Is we've attached our pulley to our wooden strengthening circle here that we've put on our plexiglass 4-foot in diameter disc. And I just want to show you here I've got 4 nuts on the outside of these 4 bolts that are sticking through. And I'm going to go ahead and lift this up and show you what it's got going on the other side. Just to make this so it's nice and stable, I'm going to put some glue in here, but these are recessed holes for the heads of those bolts, so they're not sticking out anywhere close. And in fact, they've got enough of a recession in there that I can fill that with a insulated material. That way there's no metal here right there sticking through. The only metal will actually be the bushing here. And you can see the bushing's now sandwiched, sticking out. If I get the camera angle right, you'll notice that's sticking out exactly 1/8 of an inch, which is the thickness of our plexiglass disc here. So the plexiglass disc will actually sit right there on top of this also. So in the end, everything will be riding right here on the bushing. That'll be on our 1/2 inch drive rod, and I'll show you that when we're done with it. So I'm going to go ahead now, like I told you in the last film, and I'm going to go ahead and prep the surface, get that nice and sanded up, ready to apply glue to that so we can actually glue the wooden disc. I was thinking about how to bolt through this and all that, and if I use plastic bolts it would work. It might just expand the diameter between the 2 discs too far. If I can find some good ones, I might end up putting those through on the next one, but we're going to go ahead and glue this one on as a test and to see how well it works. So let me get that done. Alright folks, so what we're doing now is actually gluing the wooden disc onto the plexiglass disc. You can see I've got cinder blocks basically packed all the way around it. I'm using those as the weight to help hold the wooden disc on while the glue dries. What we have is an actual clear epoxy that is designed to bond wood to hard plastic, and you want to make sure that it says it's designed for hard plastics. Another thing you see is the outer ring here is making sure that the outer ring of the disc itself isn't going to fold up here. I noticed the heat from the sun was kind of warping it slightly, so we might have to do something about that. Hopefully it'll turn out all right. Alright, now that we've got this gluing, once it's dry, I'll actually go ahead and take this 1/2-inch rod that you see here. We'll mount that back onto our towers, our drive tower, and we're going to set the first disc on there and see how it turns out. Then we'll go ahead and, in this same area here, we'll start building the second one, getting it glued. Each one of these are going to take 24 hours to glue, so because of the epoxy. So it's going to be 2 days before I'm actually ready to start mounting all this. And then from here, we'll start building our combs and our brushes and our large capacitor bank that we're going to use for this project. So let me go ahead and let that dry, and I'll show you the next one as it completes. Hi folks, Mr. Teslonian here. I'm going to take you through the large Wimshurst Electrostatic Generator project. We're just about done with this project. All I've got left, which I'll tell you later in the video, is just a few parts. I just wanted to kind of give you a shot here with me standing next to it to give you a height comparison. I'm 6 foot tall, so as you can tell, this is probably 6 foot something, 6 foot 2 or 3. So it's a pretty large unit. That's including the pallet height here. It dropped down a little bit, but that pallet's the actual base you'll stand on, so you're actually insulated. That way you're not going to get nailed by anything from this machine, because this machine's going to produce very, very high voltage. So I'm going to take a moment here, set up the shot, and I'm going to spin this for you for a moment, then go through and explain it to you a little more in detail. Alright folks, so here we are. We're going to go ahead and give this thing a spin and show you how it works. I'm going to need a longer handle on this. So there you go. There's our large 4-foot in diameter Wimshurst generator. The discs are now rotating in opposite directions, and we're ready to go to start building our combs and our brushes, which are the next part of this project. Seems to flow pretty well. I don't hear any grinding sounds. You notice I'm not having to turn this very fast. Alright, so there you go folks. Let me go ahead and walk you up to the thing and show you just what it looks like completed now. Alright folks, so here's a forward look at the large Wimshurst Electrostatic Generator. I just showed you a view of it in motion, so I'm going to walk you up to it now and kind of give you an overview of how I built it and what's going on here. You notice we've got a gap between the two dielectric discs. That's separated by another brass bushing in there, which I'm actually going to replace with these two nylon bushings, which will help dielectrically insulate the two plates from each other a little better. You can tell here we've got our 5-inch pulleys on either side, and on this belt we have the crossover. This will make sure that this one disc is rotating in the opposite direction than this disc over here. That's going down to our 10-inch pulley. Off of the other 10-inch pulley, what we have here is another belt. Now both of these belts are the same size. When you loop one of them over itself, it makes it obviously a lot shorter than the other one. So what I've done is incorporated here a little tensioning pulley, try to keep the other belt the same length here. So that's just your straight belt. That one doesn't loop around itself at all. This is the center drive system. You can tell it's just a 1/2-inch shaft going across. I don't even have the bracing on it. It actually holds itself there because the belt's pulling it down. I just have some notches here in the 2x4 that actually keep it kind of into place. It has some strapping that holds down on both sides here and keeps that from walking its way out of there at all. You notice the rod comes all the way to either side. This will also be another area to do other experiments. We'll actually have a pulley coming off the drive rod here, going up onto the shaft here, and this will actually turn a device inside of this area also when we're done. So we've got massive now Wimshurst discs ready to go. And so what we also have here, what I've showed you in another video, is our high voltage AC or DC generator, and that's also wired up right now, or hooked up belt wise. So we've actually got 3 10-inch pulleys down here at the bottom. These 2 10-inch pulleys going up to the Wimshurst are going into a 5-inch disc, which altogether from hand crank to the disc is about 14 to 1, 14.3 to 1 ratio here, whereas this is 45 to 1 ratio from the 10-inch here up to the 1 5/8 or 1 1/2 inch pulley that we have right here, and that's already generated quite a bit of electricity. I think we hit 117.9 volts last time I checked that. So we're ready now to start building our brushes. The brushes will actually be mounted here off the center rod in a chunk of hard plastic or a dielectric material, which will actually make sure there's a dielectric insulator between the drive rod and the brush. And the brush will actually stick all the way out, going across here, and it's going to cover a good portion of these discs. So these are going to be very wide brushes, as well as with our combs that we're going to produce. That'll be sitting out about here. They'll be mounted off this rim coming across. Those combs will sit quite a ways into these induction plates. We're probably going about this far in. So a very long, probably an 8-inch rod on either side for your combs. Alright, so now that I've showed you all that, what we're going to do now is go ahead and start completing this project. Once I get this done, we're going to set up a monster capacitor bank for this. More wired together like a Marx generator than a standard capacitor bank, which allows you to put capacity in series, in which I'll show you a film on how to build your own Marx generator as a part of this project. Until next time, I hope you enjoyed. This is Mr. Teslonian and the Teslonian Man Show. Alright folks, so what we have here is I've got the two capacitors from our last Wimshurst project. I've got a linking rod here connecting the outside aluminum foil of our capacitors to each other. Without that linking rod, this won't work. You can spin it all day long and you won't see any arcs going across. And you'll think you didn't get it to work right. That's actually a really big key to make this work. The black back there is just to make sure that there's an insulator between some of the metal parts of our AC generator and this. We'll also put insulators and dielectrics all across this whole thing, trying to isolate any extra metal from our electrostatic system. Real quickly here, let me walk you around and show you what I've done for our drive system. You'll notice here that I have two different pulleys here on the actual drive bar. Right now what we're using is small to large, and we can actually reverse that and go from large down there to the small pulley, which you can see down at the bottom of that belt down there. And that's the one we were originally using in the project. So this allows us two different speeds. We can either go very fast by hooking this one up. This gives us, it takes a lot more torque at the handle, but the RPMs are very, very fast. Or we can leave that off and we can turn this one. And I just want to show you here real quick just how much energy this takes to turn, where I'll use my one finger and we'll get that thing going. So there you go. You can actually sit there and turn that thing with one finger. You can hear the snaps in the background as it goes on. Alright, so one of the things I'm not liking about the Plexiglas is that it's extremely temperature sensitive. In the mornings the discs are pressed really tight together when it's cold, and by mid-afternoon they're spread apart again. I'm not liking that. That really doesn't allow for a very precise machine. So 1/8 inch is way too temperature responsive to be used effectively for this, at least without having to sit there and constantly wonder what the voltage difference is going to be because of the difference in distance between the plates. Later today they'll be much closer to our combs. Right now they're farther away and our voltage is a little bit lower. So there is just one of the flaws that I saw with using 1/8 inch PVC is that you're going to have to keep this in a climate controlled room to continue this working properly. So like what I've got to do now is put all of our main discharge rods. One of the things through Gauss' law that I'm looking at here is that I'm hitting a voltage limitation with this because of the size of the rod. Now this is 5/8 inch rod. The problem is that 5/8 isn't high enough to carry the actual voltage on the surface, the skin effect basically, that's being generated by this generator. So I may have to go to, like, let's say a 3/4 or a 1-inch rod right here to give me enough surface area to carry the charge that I'm looking for. And on from here, the same thing. We're going to have to build very large in diameter rods because electrostatic charge is different than normal AC or DC current, where AC and DC current typically ride inside the conductor, kind of like water inside of a pipe. Whereas electrostatic charge, there is zero net charge inside of this conductor. If you could hook a meter just to the inside of this, you'd see zero charge, even though the outside, the surface area, was completely packed full of charge. So basically, you're only using the surface area for electrostatic. No inside conductor diameter matters. It's all about surface. So we're going to increase that, like I said, to quite a large surface. I may go to 1 inch, all the way across from our pickups, all the way down to our capacitor bank. What I'm going to do real quick here is we're just going to fire this thing up and just give it a quick test spin with the original capacitors from the last Wimshurst. The problem with this is going to be is that is the biggest spark gap that I can basically get. I can go a little bigger than that due to the dielectric constant of the PVC, the thickness of the PVC and the aluminum foil, which allows only for so much charge before you start burning through the dielectric of the PVC. If I put the spark gap too much bigger than this, you turn the machine just a couple revolutions and you can actually hear a crackling sound all through the capacitors, and that's actually burn through happening, where the charge is too high, the voltage is too high for the dielectric, and it's actually burning through, creating weak spots or carbon points inside the dielectric. So that's about as big as we can go with these capacitors. Once I got some much bigger capacitors with a higher kappa material in between the induction plates, we'll be able to throw much bigger sparks from this. So let me go ahead and set up the camera and we'll turn this thing on and show you what it looks like in action. Okay, folks, so what I've got here is I got a glass of water right there. That is a plastic cup made of a dielectric material, and in it is water almost all the way up to the top. Without increasing the size of my capacitors, I was unable to increase the length of my spark. But by incorporating this glass of water between my spark gap, you should be able to witness much, much longer sparks as these sparks actually wrap around the outside edge of this cup. What is happening here is that it's actually charging the water in the cup, and the surface area of that water against the inside of that dielectric is gathering a like charge to the charge that's going across through the air as the arc. Two like charges repel each other. So it's actually allowing for a charge to build up in the cup or on the surface of the cup and allowing the arc from one ball to go across that surface over to the other ball, riding on the field created by the similar charge inside the cup. So I'm going to go ahead now and take this thing for a spin and just show you how well it works. Alright folks, that last two pictures that you saw were actually the biggest arc we produced. It was one that almost wrapped the entire cup. What I've done here is recreated it with wire. And if you kind of go back and forth, here's our first discharge point, would be actually sitting about right there for your ratio. In that shot, you can see the wire is mimicking the arc, wrapping all the way around the bottom, coming back and hitting the other discharge ball. Okay, now that we've got that cup out of that wire, you can kind of take a look at it. It wraps around, comes up, hits where that discharge ball would be. It's very, very close to what that arc actually looked like in real life for length. So what we're going to do is once again pull up our ruler here. We're going to straighten this piece of wire out to that ruler. So let's go ahead and just kind of work that out a bit here from each side and see just how long that arc really was. Well, that's pretty close right there. We don't need it perfectly straight because there's little flaws I'm either missing on the positive side of the scale of measurement or on the negative. So we're just going to take a rough estimate here. Alright, so there we go. Let me walk that up to the camera here so you can see what's going on. Hopefully over here at the end, if I get it up there, you'll notice it's a number 11. All the way down to the end there and all the way up to a number 11 here. 11-inch spark is actually going to end up being 825,000 volts. So we're looking at right there, with the backside arc that probably took place, we're definitely pushing well into the 900,000 volt range. This is really cool to see. It means with some better capacitors, we might even hit like 1.9 megavolts, something, you know, really close to that. So I thought I'd just throw this in there at the end. Until next time, I hope you enjoyed. This is Mr. Thessalonian and the Thessalonian Man Show. Hi folks, Mr. Thessalonian back here again. I want to take you through one of the most important pieces of an electrostatic generator, which is a step-down transformer. This system right here allows you to convert the very, very high voltage current that we're producing in the Wimshurst electrostatic generator to a more usable current. In this model here, what you see looks like capacitors, but these are actually what are called step-down transformers. Each one of these are wired from one of our major primary capacitors here, from the inner part of that capacitor, wired down to the inside here of this tube with aluminum foil. So basically a single layer wrap of aluminum foil around the outside of a PVC pipe, which is like a capacitor, but inside of this what we have is a coil. Wrapped and set inside of that tube, equal height in there to what's going on the outside in aluminum foil, and that's given us basically a transformer coil, but instead of like a normal transformer which has another coil on the outside of that to receive that power and transform to a lower or higher voltage, what we have here is just a capacitor coil. And then from this step-down transformer, what I have here is a brass rod making connection with the outer aluminum foil plate to the inside coil of our next step-down transformer here. And I've got our positive lead to our meter set against the outer layer of aluminum foil on this side. And you can see our negative lead running over there to the outer layer of aluminum foil on that side. And this side's also the same thing. So once again, we have nice thick copper wire running down to a coil inside of there, which I'll show you here in a minute. You can actually look down inside the pipe here. If I zoom in, you can see our copper coil kind of down in there. That's a nice thick number 6 copper ground wire right there for house grounding. That's good primary coil inside of there to help step down this high voltage current. And inside of the pipe here we've got the same thing. Maybe if I zoom in, you can kind of get a glimpse of that coil that's sitting inside of there. Alright, so what I'm going to do here real quick is I'm going to take these apart, at least one of them, and I'm going to show you what it looks like inside of a step-down transformer. And let me give you a little more of a to scale view here of what it looks like. Once again, they're just PVC pipe. This is just a connector wire here to do test off of. Don't pay attention to that. We've got aluminum foil on the outside and then coils on the inside. And what I've done is run one lead from one set of capacitors to 2 step-down transformers, and the other lead from our other capacitor to 2 step-down transformers. And from the outer 2 step-downs, what we're doing is we're going to take a reading with our meter, and we're going to see if we can't bring this voltage to something well below the 800,000 volts or 500,000 volts that it's producing at the generator in the Wimshurst. Alright folks, so what I've got here is one of our coils from inside of a step-down transformer. You can see it's just a copper coil wrapped all the way around. One thing you're going to want to do to these, because we're working with plasma, and any sharp edge is going to emit plasma and kind of ruin the effect. So you're going to want to cover this with a rubber coating. Any sharp edges on these anywhere, file them down, make sure they're nice and rounded, then cover them with an insulator of some kind. So anyways, this is actually recessed down inside of our PVC pipe, just like this. I hope you can see that in the shot there. That's actually given us, and hooked right up to our capacitor up top up there, that actually gives us the transformer effect. And because we're using electrostatic, we need an electrostatic cover or an induction plate on the outside to be able to transform this current. This is an easy way to build a step-down transformer, and like you can see, it's literally just a copper coil, piece of PVC pipe, and some aluminum foil. And you always take your measurement from the exterior aluminum foil. That's where you're going to run your power from. That's where your step-down current is. So let me go ahead and set this up. We're going to turn the generator. I'm going to show you what kind of voltage we can actually produce out of this Wimshurst. Alright folks, here we go. A test of our step-down transformer. There you go, folks. That should be a pretty good demonstration of just how well our step-down transformer bank is working. we're holding probably right around the 31, 33 volt marker. That stepped down from 300 to 400 volts from our first series of step down transformers. Alright folks, so we have our homemade Geiger counter hooked up now to our meter. We've got our ion line and our electron line now hooking down into this meter here. That's actually the meter I'm going to use, not the one that I originally showed you in the video, which is this one. It started freaking out because I got it smacked by electrostatic charge, so it always goes way up like that. So we're going to go ahead and use this one. And you'll notice there's a little tiny bit of charge still hitting off of this as the electrostatic charge inside of the Wimshurst discs here. This Wimshurst electrostatic generator that I'm using, the actual plexiglass for the disc, the dielectric, will actually hold charge for quite a while and slowly leak that charge off. And that's why you're seeing little events still sitting there. That means there's actually a small amount of radiation still being produced out of that cathode ray as that slowly bleeds down. And as an event happens, you'll notice there will actually be a little tiny spike there. So what we're going to do here real quick is we're going to set up the camera. Give me a second here, probably a little shaky. Alright, so we've got the voltmeter now hooked up, and we've got it set at AC voltage down there. Let me go over to the Wimshurst and give this a turn. Let's see if we can witness events through electrostatic voltage presence on the meter. So here we go. Alright, so let's give this thing a turn. Alright, well, as that thing winds down, that should have been enough to demonstrate any kind of interactions we were having. Oh yeah, look at those voltage spikes created as we produce X-rays, and those X-rays are being converted back into electricity in our homemade Geiger counter tube. There you go. Now as the machine slowly winds down here, like I said, there's going to be an electrostatic charge constantly leaking out of that dielectric slowly. Once that fully bleeds down, the voltage will go much lower. It actually tells me there's still rads right now being produced from this. Those discs are so large, 4-foot in diameter disc holds a lot of electrostatic charge. So that's actually still producing radiation at nice little spikes there. Thought I'd throw this in there just so you could see exactly how our homemade Geiger counter tube works and our homemade cathode tube, or cathode ray tube, actually functions and actually does produce X-rays. Until next time, I hope you enjoyed. This was Mr. Teslonian and the Teslonian Man Show.